I'm Swatisri Chavali, and my topic for presentation today is parallel processing in medical image diagnosis. Parallel processing in medical image diagnosis refers to the use of multiple processors or computing cores to simultaneously analyze and process medical images. This approach allows for faster and more accurate diagnosis of medical conditions, as well as more efficient utilization of computing resources. With the increasing complexity of medical imaging techniques, the large amount of data generated, parallel processing has become an important area of research in the field of medical imaging. Why is parallel processing important in medical imaging? Parallel processing is an important area of research in the field of medical imaging because of the increasing demand for faster and more accurate diagnosis of medical conditions. With the advent of new and more complex medical imaging techniques, such as MRI and CT scans, the amount of data generated during a single imaging session has increased significantly. This has made it difficult for traditional image processing methods to keep up with the demands for rapid and accurate diagnosis. Parallel processing can help address these challenges by allowing medical professionals to analyze and process large amounts of medical image data more quickly and efficiently. This can lead to faster and more accurate diagnosis, which can improve patient outcome and reduce the need for additional testing or procedures. Additionally, parallel processing can also help reduce the cost and time required for medical image procedures, making healthcare more accessible to patients who might otherwise be unable to afford it. The use of parallel processing in medical image diagnosis has the potential to revolutionize the field of medical imaging and improve the quality of care for patients around the world. This presentation will cover the topic of parallel processing in medical image diagnosis. It will begin by defining parallel processing and explaining its relevance to medical imaging. Next, it will discuss some of the challenges faced by medical professionals when diagnosing medical images and how parallel processing can help address these challenges. The presentation will then provide examples of medical imaging techniques that use parallel processing and present a case study to demonstrate benefits of this approach. Additionally, the presentation will discuss some of the future directions for research in parallel processing for medical image diagnosis and the potential impact of future development in this area on medical imaging as a whole. Finally, the presentation will conclude by summarizing the main points covered and encouraging further research and development in this important area. What is parallel processing? Parallel processing is a method to solve large problems that can be divided into smaller ones, which can be solved simultaneously and has been widely used. Parallel processing is a computing technique that involves dividing a large task into smaller, more manageable subtasks that can be processed simultaneously using multiple processors or computing cores. In other words, it involves breaking down a complex problem into smaller parts and solving them concurrently, which can significantly improve the efficiency and speed of computation. Parallel processing works by dividing a problem into smaller tasks, assigning each task to a separate processor or computing core, then combining the results of each task to produce a final output. This approach is often used in applications where large amounts of data need to be processed quickly, such as medical imaging. In medical image diagnosis, parallel processing can be used to process large volumes of data simultaneously, allowing medical professionals to make more accurate and timely diagnosis. This can be especially important in cases where time is of the essence, such as in emergency medical situations. Parallel processing is a powerful technique that can help improve the speed and efficiency of computation in a wide range of applications, including medical imaging. Here are some everyday examples of parallel processing. Multi-core CPUs. Modern computers often use multi-core processors, which allow for parallel processing of multiple tasks simultaneously. For example, a quad-core CPU can process 4 tasks at the same time, while an 8-core CPU can process 8 tasks simultaneously. Graphics processing units. GPUs are specialized processors designed to handle graphics and video processing tasks. They use parallel processing to quickly render complex images and videos, making them ideal for gaming and other graphics intensive applications. Internet data transfers. When you download a large file, the data is often split into smaller chunks and sent over multiple connections simultaneously. This allows for faster download times by utilizing parallel processing to transfer the data. Image and video editing. Image and video editing software often use parallel processing to speed up the rendering and processing of complex visual effects. Machine learning and AI. Machine learning and artificial intelligence algorithms often use parallel processing to analyze large data sets and identify patterns and trends more quickly and accurately. Parallel processing is an essential technique used in many everyday applications, making it a critical area of research in computer science and engineering. Application of parallel processing in medical image diagnosis. Parallel processing can be applied to medical image diagnosis in several ways. One common approach is to use parallel processing to accelerate the processing of medical images and improve the accuracy of diagnosis. For example, medical images generated by MRI or CT scans can be very large and complex, which can make it difficult for single processor to analyze and process data quickly. By using parallel processing, the data can be divided into smaller subsets and processed simultaneously by multiple processors or computing cores. This can significantly reduce the time required to analyze and process medical images, making it possible to diagnose medical conditions more quickly and accurately. Parallel processing can also be used to develop machine learning and AI algorithms that can analyze medical images and identify patterns, trends more quickly and accurately than traditional image processing techniques. For example, deep learning algorithms can be trained to recognize specific features in medical images that are associated with certain medical conditions, making it possible to automate the diagnosis process. Finally, parallel processing can be used to improve efficiency of medical imaging systems by reducing the time and resources required for image processing. This can lead to faster and more affordable medical imaging procedures, making healthcare more accessible to patients who might otherwise be unable to afford it. Parallel processing is a powerful technique that can help improve the speed, accuracy, and efficiency of medical image diagnosis, which can ultimately improve patient outcome and reduce healthcare costs. Here are some challenges in medical image diagnosis. Large volume of data. Medical images generated by MRI or CT scans can be very large and complex, making it difficult for medical professionals to process and analyze the data quickly and accurately. Image quality. Medical images can sometimes be of poor quality due to factors such as patient movement or inadequate imaging parameters, which can make it difficult to identify important details. Variability in images. Images can widely vary depending on factors such as imaging techniques, equipment, and patient characteristics. This can make it challenging for medical professionals to identify patterns or changes that may indicate a medical condition. Limited training data. In some cases, medical professionals may have limited access to training data or experience in interpreting certain types of medical images, which can make it difficult to accurately diagnose certain conditions. Time constraints. In emergency medical situations, medical professionals may need to make quick diagnosis based on limited information, which can be challenging and stressful. These challenges can make it difficult for medical professionals to diagnose medical conditions accurately and quickly. However, new developments in image processing and machine learning techniques such as parallel processing are helping to address some of these challenges and improve the accuracy and speed of medical image diagnosis. Here are some traditional image processing techniques. Pre-processing. Before applying any image processing technique, the image needs to be pre-processed to remove noise, correct distortion, adjust brightness and contrast, and then other factors. This can be a time-consuming task, especially for large images. Feature extraction. Feature extraction involves identifying important regions or features in an image that can be used to analyze and understand the image. This can be a time-consuming process, especially for complex images that require advanced techniques. Segmentation. Image segmentation involves dividing an image into different regions or objects. This is often a challenging task, as it requires identifying boundaries between objects in the image. This process can be time-consuming, especially for large images. Classification. Image classification involves identifying the category or class to which an image belongs. This is often done using machine learning algorithms that require extensive training on large data sets. The training process can be time-consuming, especially for complex image classification tasks. Post-processing. After applying any image processing technique, the image may need to be post-processed to improve the results or to remove artifacts introduced by the processing technique. This can be a time-consuming task, especially for complex images that require advanced techniques. Traditional image processing methods can be time-consuming due to complex nature of the processing techniques and large amount of data that needs to be processed. Benefits of parallel processing in medical imaging. Here are some benefits. Faster processing times. Medical image diagnosis often involves processing large volumes of data, such as CT or MRI scans, which can be time-consuming Parallel processing can help speed up image analysis, resulting in faster diagnosis and treatment planning. Improved accuracy. Parallel processing can help improve the accuracy of medical image diagnosis by enabling the use of more advanced image analysis techniques. By processing images in parallel, it is possible to analyze more complex features of the image, which can improve the accuracy of diagnosis. Parallel processing can help improve the efficiency of medical image diagnosis by enabling the use of automated image analysis tools. By automating image analysis, it is possible to process large volumes of images more quickly and accurately, allowing healthcare providers to focus on aspects of patient care. Cost savings. Parallel processing can help reduce costs associated with medical image diagnosis by enabling the use of more efficient hardware and software. By using parallel processing techniques, it's possible to reduce the hardware requirements for image analysis, which can help reduce costs. Enhanced collaboration. Parallel processing can help facilitate collaboration among healthcare providers by enabling real-time sharing of medical images and analysis results. By processing images in parallel, it is possible to quickly share analysis results with other healthcare providers, enabling them to make more informed decisions about patient care. Parallel processing offers several benefits of medical image diagnosis, including faster processing times, improved accuracy, increased efficiency, cost savings, and enhanced collaboration. These benefits can help improve patient outcome and reduce costs associated with medical image diagnosis. Here are some existing medical imaging techniques that use parallel processing. Computed topography. CT scans use X-rays to create detailed images of the body. CT scanners typically use parallel processing techniques to reconstruct the images, which involves processing large volumes of data. Parallel processing can help speed up image reconstruction, resulting in faster diagnosis and treatment planning. Magnetic resonance imaging. MRI uses powerful magnets and radio waves to create detailed images of the body. MRI scanners often use parallel processing techniques to reconstruct the images, which can involve processing large volumes of data. Parallel processing can help improve the accuracy and speed of image reconstruction, resulting in more precise diagnosis and treatment planning. Positron emission tomography. PET scans use radioactive tracers to create images of the body's metabolic activity. Scanners often use parallel processing techniques to reconstruct the images, which involves processing large volumes of data. Parallel processing can help improve the accuracy and speed of image reconstruction, resulting in more precise diagnosis and treatment planning. Ultrasound imaging. Ultrasound uses high-frequency sound waves to create images of the body. Ultrasound scanners often use parallel processing techniques to process the images, which can involve analyzing large amounts of data. Parallel processing can help improve the accuracy and speed of image analysis, resulting in more precise diagnosis and treatment planning. Digital pathology. Digital pathology involves the analysis of tissue samples using digital images. Digital pathology systems often use parallel processing techniques to analyze large volumes of images, which can involve identifying and analyzing complex features of the images. Parallel processing can help improve the accuracy and speed of image analysis, resulting in more precise diagnosis and treatment planning. Overall, parallel processing plays an important role in many medical imaging techniques, enabling faster, more accurate, and more efficient image analysis. Here is a case study. One case study that demonstrates the benefits of using parallel processing in medical image diagnosis involved the analysis of MRI images for the diagnosis of Alzheimer's disease. Researchers at the University of California, Los Angeles, UCLA, used a parallel processing approach to analyze MRI images of patients with Alzheimer's disease. The study involved analyzing the volume of hippocampus, a region of the brain that is commonly affected by the Alzheimer's disease. The researchers used a parallel processing algorithm to automatically segment the hippocampus and measure its volume. The study found that the parallel processing approach was significantly faster than traditional methods of manual segmentation. The parallel processing algorithm was able to segment the hippocampus in less than 5 minutes per patient, compared to 20 to 30 minutes per patient using manual segmentation. The parallel processing approach also demonstrated high accuracy with correlation coefficient of 0.95 between automated and manual segmentation results. The benefits of using parallel processing in this study included faster image analysis and improved accuracy, which could help facilitate earlier and more accurate diagnosis of Alzheimer's disease. The study also demonstrated the potential of parallel processing to enable the use of automated image analysis tools, which could help improve the efficiency of medical image diagnosis. Overall, this case study demonstrates the potential benefits of using parallel processing in medical image diagnosis, particularly for the analysis of large volumes of data such as MRI images. By using parallel processing techniques, it's possible to improve the efficiency and accuracy of image analysis, resulting in better patient outcomes. Implications from this case study. The case study that demonstrated the benefits of using parallel processing in medical image diagnosis showed that this approach could significantly improve the speed and accuracy of image analysis. In particular, the use of parallel processing in the analysis of MRI images for the diagnosis of Alzheimer's disease demonstrated a correlation coefficient of 0.95 between automated and manual segmentation result, indicating high accuracy. Furthermore, the parallel processing algorithm was able to segment the hippocampus in less than 5 minutes per patient compared to 20 to 30 minutes per patient using manual segmentation. The results have important implications for medical professionals. By using parallel processing in medical image diagnosis, medical professionals can significantly improve the speed and accuracy of image analysis, enabling faster and more accurate diagnosis and more effective treatment planning. This could lead to better patient outcomes and improved healthcare efficiency. One of the key advantages of parallel processing is its ability to handle large volumes of data in a short amount of time. Medical professionals can leverage this advantage by analyzing large sets of medical images with greater accuracy and speed, thereby improving patient outcomes. Additionally, parallel processing can enable the development of automated image analysis tools that can reduce the burden on medical professionals and improve the efficiency of medical image diagnosis. Another important implication of the case study is that it highlights the importance of adopting new technologies and methods in medical image diagnosis. Medical professionals should consider integrating parallel processing algorithms and other advanced technologies into their diagnostic workflows to improve the speed and accuracy of image analysis. By embracing these new tools, medical professionals can stay up to date with the latest advances in medical imaging, provide better care to their patients. Future research in parallel processing. Parallel processing has already shown great promise in medical image diagnosis, enabling faster and more accurate image analysis. However, there is still much room for future research and development in this area. Some potential future directions of research in this area are developing new parallel processing algorithms. There's a need to develop new improved parallel processing algorithms that can handle increasingly complex, diverse medical imaging data. These algorithms should be designed to handle a wide range of image modalities, including CT, MRI, PET, and ultrasound. This should be optimized for speed and accuracy. Integrating artificial intelligence and machine learning. Artificial intelligence and machine learning have shown great promise in medical image analysis, and integrating these techniques with parallel processing could lead to even more accurate and efficient diagnosis. ML algorithms can be used to train parallel processing algorithms to recognize patterns in medical images and make accurate diagnosis more quickly. Developing cloud-based solutions. Cloud-based solutions could be used to allow medical professionals to access powerful parallel processing capabilities from anywhere in this world. This could enable medical professionals in remote or undeserved areas to access state-of-the-art image analysis tools, improving healthcare outcomes for patients in these areas. Incorporating 3D imaging. Many medical imaging applications, such as surgical planning, require 3D imaging data. Parallel processing could be optimized to handle 3D imaging data, enabling faster and more accurate 3D image analysis. Enhancing cybersecurity and privacy. As medical imaging data becomes more increasingly digitized, there's a growing need for robust cybersecurity and privacy measures to protect patient data. Future research in parallel processing of medical image diagnosis should consider ways to enhance cybersecurity and privacy while maintaining the speed and accuracy of image analysis. Future research in parallel processing for medical image diagnosis will likely focus on developing new and improved algorithms, integrating the AI and ML, leveraging cloud-based solutions, incorporating 3D imaging, and enhancing cybersecurity and privacy. These advances will enable medical professionals to provide faster and more accurate diagnosis and improve patient outcomes. Here are some of the potential areas of improvements. Algorithms. The development of new and improved parallel processing algorithms is critical for improving the speed and accuracy of medical image analysis. Future research should focus on developing algorithms that can handle increasingly complex medical imaging data while minimizing errors and reducing processing times. Hardware. The availability of high performance computing hardware, such as GPUs and FPGAs, has greatly improved the efficiency of parallel processing. However, further advances in hardware, such as development of more powerful and energy efficient GPUs and FPGAs, could lead to even faster and more accurate medical image analysis. Integration of AI and ML. Integrating AI and ML into parallel processing algorithms could significantly improve the accuracy and efficiency of medical image diagnosis. Future research should focus on developing ML algorithms that can learn from large volumes of medical imaging data and improve the performance of parallel processing algorithms. Cloud-based solutions. The use of cloud-based solutions could enable medical professionals to access powerful parallel processing capabilities from anywhere in the world, improving the healthcare outcomes of patients in remote or undeserved areas. Future research should focus on developing cloud-based solutions that are secure, efficient, and that can handle large volumes of medical imaging data. 3D imaging. Incorporating 3D imaging into parallel processing algorithms could improve the accuracy and efficiency of medical image analysis for surgical planning and other applications. Future research should focus on developing parallel processing algorithms that can handle 3D imaging data efficiently while minimizing processing times and errors. Cybersecurity and privacy. As medical imaging data becomes increasingly digitized, there is a growing need for robust and cybersecurity and privacy measures to protect patient data. Future research should focus on developing new improved cybersecurity and privacy measures such as encryption and secure data sharing protocols to ensure that patient data remains protected. Overall, improving algorithms, hardware, integrating AI and ML, developing cloud-based solutions, incorporating 3D imaging, and enhancing cybersecurity and privacy are all potential areas of improvement in parallel processing for medical image diagnosis. Addressing these areas could lead to faster, more accurate diagnosis and improved healthcare outcomes for patients. Potential impact of future development in this area. Faster and more accurate diagnosis. Parallel processing algorithms can handle large volumes of medical imaging data quickly and accurately, have the potential to significantly improve the speed and accuracy of medical image diagnosis. This could lead to faster and more effective treatment for patients and improved healthcare outcomes overall. More efficient use of resources by enabling faster and more accurate medical image analysis, parallel processing algorithms could reduce the need for expensive and time-consuming imaging procedures, such as repeat scans and invasive procedures. This could lead to more efficient use of healthcare resources and cost savings for healthcare providers. Improved accessibility. Cloud-based solutions and other advances in parallel processing for medical imaging could make advanced image analysis tools more accessible to medical professions around the world, regardless of their location and access to expensive hardware. This could help in address disparities between healthcare outcomes between different regions and populations. Enhanced research capabilities. Parallel processing algorithms could enable researchers to analyze large volumes of medical imaging data more quickly and accurately, leading to more rapid advances in medical research and improved understanding of disease processes. More personalized medicine. By enabling faster and more accurate diagnosis, parallel processing for medical imaging could help to enable more personalized medicine tailored to the specific needs of individual patients. This could also lead to more effective treatments and improved healthcare outcomes. The potential impact of future development in parallel processing for medical imaging is significant. Faster and more accurate diagnosis, more efficient use of researchers, improved accessibility, enhanced research capabilities, and more personalized medicine are just some of the potential benefits of future advances in this area. By improving the speed and accuracy of medical image analysis, parallel processing could help to transform field of medical imaging and improve healthcare outcomes for patients around the world. The importance of parallel processing in medical imaging diagnosis cannot be overstated. As medical imaging data becomes increasingly complex, the ability to process and analyze large volumes of data quickly and accurately is critical for enabling faster and more accurate diagnosis, improving healthcare outcomes, and advancing medical research. Parallel processing algorithms and hardware have already demonstrated significant benefits in medical imaging, enabling faster and more accurate diagnosis, reducing processing times, and improving the efficiency of healthcare providers. However, there is still much room for further research and development in this area. Improving algorithms, hardware, and incorporating artificial intelligence and machine learning could lead to even greater improvements in the speed and accuracy of medical image analysis. Developing cloud-based solutions and enhancing cybersecurity and privacy measures could also help to make advanced image analysis tools more accessible to medical professionals around the world, regardless of their location, to access expensive hardware. In short, further research and development in parallel processing for medical image diagnosis is essential for improving healthcare outcomes and advancing medical research. The potential benefits of future developments in this area are significant, and the field of medical imaging stands to benefit greatly from continued investment in this area. Encouraging further research and development in parallel processing for medical image diagnosis is therefore of utmost importance, both for the medical community and for the patients around the world. Thank you.